Okay, good morning. So in the last lecture we started looking at types in Haskell, and we introduced different ways of defining new data structures. We had a type synonym using the word type, and we had a data keyword introducing new data structures. And we also discussed about polymorphism, and there are two types of polymorphism. One type is you use the same implementation for functions with the same name but arguments of different types. And to use this, you need the concept of type variables. And the other kind of polymorphism was ad hoc polymorphism. And there the idea was to have type classes. And in these type classes, you define certain functions. And then the types that are a member of these type classes, they implement these functions. But every type can implement the function in a slightly different way. We've seen one example using a function called, using a type class called ek. Let me show you another example. So another example for a type class to recapitulate this idea. An example for a type class is the type class show. So this type class is just like ek. This is another predefined type class. And the idea of this type class is those types should be member of this type class where the objects can be printed on the screen. So whenever you type in some expression into your interpreter and you press return, then the interpreter will try to evaluate this expression and it will try to print the result on the screen. Now, in order to print the result on the screen, well, on the screen you cannot print arbitrary data objects. On the screen you can basically only print strings. So this type class contains those types whose objects can be printed on the screen. And in order to print them on the screen, Haskell uses a function called show with a small s. So there's a function show which transforms objects into strings, and whenever you do some evaluation and you want to print something on the screen, not the object itself is printed, but show is applied to this object. This gives you a string, and this string is printed. So the class show is defined like this. It is a class, and in this class there are several functions, but in particular there's a function show with small s. So this is a type class, therefore it's written with a capital S. This is a function, therefore it's written with a small s. And, show A, of course. So this means if a type A is member of the type class show, then we have the following functions. There is a function called show, and that would be a function from A to string. And there are some other functions. And so this means whenever A is a member of this type class, then there exists such a show function which converts objects of this data type into strings. And if an expression is evaluated in the interpreter, then after evaluation, the function show is called to convert the result into a string, and the string is printed. And if the type of the expression does not belong to the type class show, then you get a program error. So if an expression is evaluated in the interpreter, then afterwards the function small show is called to convert the result into a string, and this string is printed on the screen. The result into a string, which is then printed on the screen. So let's make some examples. I mean, for most of the predefined data types that we know, they are member of this type class. So bool is a member of show, int is a member of show, because indeed if you have a Boolean expression or an integer expression, they can be printed on the screen. So such a function show exists for all these types. If you define your own types, then if you want to be able to print expressions from these types on the screen, then you have to declare that they should also be a member of the type class show. So let's look at an example. Let's look at our data structure for lists, non-predefined but user-defined. If we want to define lists ourselves, we did that in the last lecture. We would say there is a new data type, list A. So list is a new type constructor of arity 1. It takes a type, gives you a new type. And lists are either constructed with this data constructor nil, or with the data constructor cons, which takes two arguments of type A and list A and gives you back a list. Now, if you write algorithms which operate on this list data structure, and then you want to evaluate them in your interpreter, then you get a program error because the interpreter does not know how to represent lists on the screen. So the interpreter really needs a function to convert objects of type list A into strings. Now there are two possibilities. One possibility is to really declare that list A should also be a member of this type class show by using such an instance declaration as we've seen in the last lecture. If you want to do it the easy way, you can instead add these words in the end of your type declaration. And this means if you add the word deriving and then the name of a type class, then this has the same effect as if you write that list A should be an instance of the class show. But then, of course, how to implement these functions here? Well, Haskell will take a standard implementation and will, for example, for show, it will simply print the words cons and then the string for the first element, and then it will print the remaining list. So this means it declares that list A is an instance of the type class show, and to implement the functions of this type class, Haskell automatically generates default implementations. It generates default implementations for the functions of the class. So, and you can do this with certain predefined type classes. You can also write deriving ek, or there are some other predefined classes where you can do this as well. So this is the short way of doing it. But if you want to influence how lists are printed on the screen, maybe you want to print them in a different way, then you can define this show function yourself, and you can declare that list A should be a member of type class show and say how lists in fact should be printed on the screen. So the alternative would be to do it like this. So if you don't write deriving show, then instead you would declare that lists should indeed be members of the type class show. How would that work? You would say, well, list A should be a member of the type class show, and then you say how this function small show should be implemented. Now, do we really want to have every type list A be a member of the type class show? Well, the problem is, how would you print lists on the screen? In order to print lists on the screen, you also want to print the elements of the list. And therefore, the elements of the list, they should also be of a type which is member of show, otherwise you don't know how to print these elements. So not all types list A should be member of this type class, but only if A is also a member of this type class. So if A is a type which you can print on the screen, then list A should also be a type which you can print on the screen. This was this idea of having contexts. So such contexts, which you can see by this double arrow, they mean for this type variable this type variable can only be instantiated with types that come from this type class. So this means if A is a member of type class show, then list A should also be a member. And now we can say how show should be implemented. And, well, now you can print lists in a way that you think lists should look like on the screen. For example, you could say, instead of nil on the screen, I want to see the following string. I want to see the string which looks like this. And you can now see how we can make our own lists behave like predefined lists. I mean, just by defining the show function in an appropriate way, our own defined lists will look like predefined lists when you see them on the screen. Now, but I will make a very easy, so, well, anyway, we can then say, how do we represent lists which are not empty on the screen? Well, here we could say we want to represent them like predefined lists, so we would print the first element, then we would print a colon, and then we would print the remaining list. So this would be done like this. We would first print, this would be the string, which first gives us the first element, the string which represents the first element. Then it will give us maybe a space and then a colon, and then it will give us the remaining list. So what does this mean? This means this is a string. This is a string which is the representation of the first element, and this show function here is not necessarily the same show function that we define here, but it's the show function which depends on the type of this element. So if this is an integer, then Haskell will look how show is defined for integers. If this is a Boolean, then Haskell will use the implementation of show for Booleans. So the implementation of this show depends on the type of x. So depends on the type A. So this is a string. This is also a string, the string which just contains two blanks and a colon. And this is also a string, namely the string which corresponds to the rest of the list. And this is the append function which simply concatenates lists. Strings are characters of lists, so this whole thing is a big string. And in this way, we can say how lists should be converted into strings. And if you define it like that, then whenever you write an algorithm which operates on your own lists, then the interpreter will, in the end, give you the result on the screen. And the result on the screen will look like this. So it will consist of square brackets and of colons. This is the way you can then see it on the screen. Okay, so this also indicates why these contexts can be useful in instance declarations. Now, we have seen these contexts in instance declarations. We have seen them also in other forms of declarations. We have not yet seen them in class declarations. So, as you can see in the grammar, you can add these contexts when you declare an instance, and we did that just here. You can also add them when you declare classes. And this can be useful in order to have classes and subclasses. So this is something related to concepts you know from object-oriented languages where you have classes and subclasses and superclasses. And why this can be useful, I will also try to show you with an example. Having these contexts in class declarations can be used in order to have hierarchical kind of hierarchical organization of type classes. So these type classes do not have to be completely unrelated, but they can be related. You can say, well, a certain class is a subclass of another class. So, for example, in Haskell, apart from the type classes ek and show, there are some other type classes. For example, there is a type class ort. And in this type class ort, we want to have those types where the elements can be ordered. So these should be the types where we have operators like greater or smaller or greater equal or smaller equal. And obviously not for all types this makes sense. So for example, for functions it is very difficult to say why you would want them ordered. But for integers it makes sense. For characters it makes sense as well, because you can order characters according to the ASCII numbers which correspond to the character, and so on. So these should be the types which have functions like greater or smaller or greater equal or smaller equal, and so on. And, well, you can easily, if you look at this, obviously, whenever you have a type which has these operators, then the type should also have the operator equal and not equal, because what is equal? Equal simply means greater equal and smaller equal. So if x is greater equal than y and y is smaller and x is smaller equal than y, then x and y are equal. So it makes sense to say only those types where we have equality may also be a member of ORT. On the other hand, not all types where we have equality should also be a member of ORT. For example, lists. Well, for lists, equality makes sense, but why? But how to compare lists? Well, there are different ways to compare lists, but it's not necessarily clear why lists should be member of ORT. So the idea would be only types that are in the type class ek may also be in ORT. So in other words, ORT is a subclass of ek. So you want to make sure that if someone declares that a type is member of ORT, then he also has to make sure that this type is a member of ek. And in order to ensure this type class ORT would be defined like this. You would not just say ORT is a type class where you have certain operators, like, for example, greater and smaller, which have the type A to bool. You can also say how these things are implemented. For example, x smaller than y might be implemented in the following way. X is smaller than y whenever x is less or equal than y and x is not equal to y. Now this operator is an operator which exists for all types which are member of ek. Ek is the type class for equality and disequality. This is disequality. So if A is a member of type ek, then you know that this thing exists. So it's fine to write it like that, but we want to make sure that not all types can be member of ORT, only those that are also member of ek, and therefore we need this context here. So we write it like this, and this means there's a new type class ORT, and A can be a member of ORT, and then A has these functions, but this is only possible if A is also a member of ek. And now we have this hierarchical organization which simply says, if A is a member of ek, then probably A is also a member of ORT. But it cannot be that it's in ORT and not in ek. And, well, in this way you have some further type classes. For example, there's another type class, num, for numbers. There's also, this type class would look like this. So if A is a member of ek and A is a member of show, then probably A can also be a member of the type class num. And this is the type class for numbers. So this is a type class for numbers. So this type class contains types like int, but also types like float, and so on. And there we would have functions like plus and minus and so on. They would be defined here. They would have the type A to A to A. So knowing this, now you can also imagine what in reality the type of something like 1 is. So up to now we have always said 1 is of type int. Now that's not true in Haskell. 1 can be of type int, but it can also be a floating point number. 1 is also a perfectly legal float. So you don't know really what 1 is. 1 is a number, but it can be an integer, interpreted as an integer number or as a floating point number. And Haskell has some more data types like double and so on. It's like in other programming language, like Java has float and double for different precision when doing floating point arithmetic, and it's similar in Haskell. So the type of 1 is, you don't know, it can be any type which is member of the type class num. It can be int, it can be float, it doesn't matter. So the type of this is not int or float, but it is this. So it is an arbitrary type, provided this type is member of num. So that's the real type of something like 1 or 2. So if you type in Hux, you want to find out the type of 1, this is what Hux will tell you, and that's the reason. So this means 1 can be both an integer or a floating point number. And there are some more predefined type classes, but of course you can also define type classes yourself. Okay, so this is what I wanted to say about type classes and about types in particular. And this ends the introduction of the Haskell language. So now we have basically introduced all of the syntax that is needed. There will be a little more additions later on, but basically this is it. And now, so you see it's not too much. And now the question is, how can we program with this in a nice way? And in the next 3 sections, I will illustrate 3 particular ways of programming which you can do in functional languages like Haskell and which you don't really do in other languages. And they, of course, use certain features of the language, but they don't introduce much more. So you just use these features and then program in a certain way. And so one thing I want to show you is, that will be the next section, is how to program with higher order functions. And then I want to speak about how to program, how to exploit lazy evaluation and to program in particular with infinite data objects. So programming with lazy evaluation and infinite data objects. And the last section that I want to spend on how to program in functional languages is to speak about the concept of monads. And with these monads, you can, for example, do input and output. Because up to now, you don't really know how to do this. You can type in expressions into your interpreter and you press return, then you get a result. But how to read input from a file, or how to read input from the keyboard, and how to print something again to a file, you don't know. And that's particularly interesting in languages like this. So it's not just saying read or write and that's it, but it's much more interesting, and therefore I will speak about this. And this is a concept which you can also use for other kinds of programs. So these are programming techniques in functional programs. So this is what we'll do in the next few lectures, and then afterwards I will speak about the concepts that lie behind functional programming and how to, in fact, implement functional programming languages, how to implement, for example, compilers or interpreters, how to do type checking, how to define the semantics of a functional language. Okay, so first thing, that of these 3 main techniques that are possible in functional programs and not really possible or not really used in other languages, I want to speak about higher order functions. So what's a higher order function? A higher order function is a function where the argument or the result is again a function. So a higher order function is simply a function whose argument or result is again a function. So these are functions which do not operate on integers or booleans, but on functions again. It's again a function. Okay, so for example, if you have a function like square, which goes from int to int, you can see the argument is of type int, the result is also of type int, so this is not a higher order function. This is called a first order function. But if you have a function like plus, which takes an integer and another integer and gives you an integer, this is nothing else but writing it like that. So it takes an integer as argument, that's not a function, but it returns a function. As you might remember, plus 2 gives you the function which waits for an integer and then increases this integer by 2. So the result is a function. So this is already a higher order function because the result is indeed a function. The argument is not a function, but the result. So we have already seen higher order functions. But do we also know functions where the argument is again a function? Well, we haven't seen something like that yet in the lecture, but even from high school mathematics, you are used to such functions. So it's not so unusual. And the most familiar higher order function where the arguments in fact are functions, which you already know, is function composition. So this is a function that you are familiar with. This is predefined in Haskell, and it's just written with a dot. And the idea of function composition is you take two functions, and the result is the function which composes the functions. So in mathematics, you have something like this. F circle G, F and G are functions, and the result of this is again a function which will first apply G and then apply F. So in mathematics, you would write it like this. And obviously, this circle here is a higher order function because it takes two functions as input. The arguments here are F and G, which are functions, and the result is again a function, namely the composition. And as I said, this is predefined in Haskell, but it's not written with a circle, but with a dot. So the definition of this in Haskell looks like this. So dot is an infix operator which associates to the right and which has highest binding priority. And it is defined like this. So it is defined like this. So it takes two functions, F and G. Now what should be the types of F and G? Now suppose G has type A to B. Then what should be the type of F? B to C, right? And what would be the type of the result? A to C. Okay. So the type of this is F has the type B to C, G has the type A to B, and the result will have the type A to C. And now you can see, obviously, the argument is a function. So this takes, as first argument, a function from B to C, and then it's carried, so the result is a function which again takes a function and returns another function. So this is indeed something which takes a function as input and gives you a function as result. And how is it defined? So how would we define f dot g? Any idea? So the outcome of this should be the function which, if you give it an argument, it will first apply g and then it will apply f. Now how can we write down a whole function in just one single expression? Mm-hmm. If we write fg behind each other, then what does that mean? Right, this would mean that g is an argument of f. This would mean apply f to the argument g. That's not what we want. And that's also not allowed because f has the type b to c. G, and so this function f can only be applied to arguments of type b. But g has this type. It's not type b, it's a strange function type. So something like this is not type correct. This you may not write. So we have to modify this a little bit. Mm-hmm. Right. So this is the function lambda x equals f of gx. And now, to make this sound, we have to write parentheses like this. So this is the function which waits for an argument x. X has the type A. So it waits for an argument of type A. Then, if you have this argument, it will first apply g. G is a function from A to B, so this will have type B. And then it will apply f. F is a function from B to C, so this thing will have type C. So it's indeed a function from A to C, and that's as desired. So you can see that this lambda is here used to express a whole function as one single term, as one single expression. And we need these parentheses because function application associates to the left. So if we write this without function application, it would mean first apply f to g, and then apply the resulting thing to x. That's not what we want. We want to apply g to x first. So here we need parentheses. So what would happen if we apply this in an example? Let's assume we define half and square as before. So half's a natural number, squares it. And now we apply this higher order function to compose half and square. And then we apply this to some integer 4. So what would happen? Well, it would happen, this function is the function which first squares an argument and then divides it by 2. So the result would be this squared and then divided by 2, so it would be 8. Or maybe another example. Let's say we take this function. So it's this lambda function, and we compose it with square, and then apply it to 5. Then what do you think will be the result? Mm-hmm. 26. You first square this 5, which gives you 25, and then you apply this function. This is the function which takes an argument and adds 1. So if you add 1 to 25, you have 26. Okay, so this is the general idea of higher order functions, and you can see that higher order functions are not so unnatural because function composition is something you are used to anyway. Now, what are higher order functions really good for? Why can they be used to write nice programs? And that I will show you next. The reason why higher order functions can be useful for programming is that there are many algorithms which work in a very similar way. And instead of implementing all these algorithms separately, you can now try to extract the general structure of these algorithms. And this general recursion structure of these algorithms you implement with a higher order function. So the higher order function implements a certain form of generic algorithm, and then you can instantiate this generic form by certain parameters and reuse this certain form for specific applications. So the general reason why higher order functions are interesting is, so the use of higher order functions for programming, the main use is one can use higher order functions to implement certain patterns or certain recursion structures. And they can be reused many times for different specific algorithms or for different applications. So the advantage is you gain, you get smaller programs, they are reusable, they are better readable, so it increases readability, reusability, and so on are increased. And to show you what I mean, I will now show you 3 examples of common algorithms which operate in the same way, and we try to abstract the general principle out of these algorithms and implement this general principle on its own by a higher order function, and then you can see that these specific algorithms can then be implemented in a much shorter and much more readable way. And the first and simplest of these higher order functions which implements a certain type of algorithm is the function map. So I will give you 3 examples. And the first example is the function map. Now to motivate this, let's look at the following example. So here we have 2 functions, sucklist and square root list, which do similar but different things. So what they do is the following. So sucklist takes a list of integers and increases all these integers by 1. So if you apply sucklist to the list 1, 2, 3, then what happens is you get the same list, but every number in here is increased by 1. So you get the list 2, 3, 4. And here this function suc that I wrote here, this should be a function from int to int, which simply increases its argument by 1. So you can define it like this. This is plus 1. And then how does this sucklist function work? Well, if you apply sucklist to the empty list, you get the empty list. If you apply sucklist to a list which is not empty, then you increase the first argument by 1 by applying this function suc, and you call sucklist recursively on the rest of the list. Now the next function, square root list, does something completely different. So square root list does not operate on integers, on lists of integers, but lists of floating point numbers. And it does not increase the numbers, but it computes the square root. So suppose you have something like 4 and 25 and 100. Then it will give you back the list which computes the square roots of these elements. So the square root of 4 is 2, of 25 is 5, and of 100 is 10. Square root is predefined in Haskell. Now how does this function operate? If the argument is the empty list, you get back the empty list. If it's not empty, then you apply the function square root on the first element, and you call square root list recursively on the rest of the list. Now, obviously these 2 algorithms do different things, but if you look at them, you can see, well, they are somehow similar. They both follow the same principle. They take a list and they apply a function on all arguments of the list. So basically, they look whether the list is empty, and if the list is empty, they again return the list. And if the list is not empty, then they apply a certain function on each element of the list. Here they apply the function suc. There, the function square root is applied, so that's different. But what happens is you apply a certain function on every element of the list, and that's it. And now by seeing that these algorithms are rather similar, one can try to abstract from the differences. So both algorithms follow the same recursion structure. So I have the same structure, and basically what they do is apply a certain function, and one time is it suc, and the other times it's square root on all elements of a list. And these elements, well, one times these elements are integers, and one times they are floating points of a list. And so the idea now is, let's try to abstract from the differences that we have between sucklist and square root list, and implement one general algorithm which somehow subsumes both of these algorithms. So abstract from the differences between these two algorithms, between suck list and square root list, and implement this form of algorithm as a general algorithm, and that will be a higher order function. And implement this structure as a general function. As a general, and this will be a higher order function. So, what are the differences? Well, there are two differences. One difference is that suck list operates on lists of integers, square root list operates on lists of floats. So if we want to implement a generic function which subsumes both, we should implement it in such a way that it can be used both for integers and for floating point numbers. And so the idea is, let's abstract this to a type variable. So this difference will be abstracted by using a type variable, A. And the other difference is this. So suck list applies the function suck on each element. Square root list applies the function square root on each element. So to have something more general, we can say, well, apply any function on the elements of the list. So here, instead of using these actual functions, we just use a variable which stands for a function. So here we use a function variable, G. So if we in general want to write a generic function which does the same thing as suck list and square root list, it would therefore look like this. It would just operate on lists of integers or lists of floating point numbers, but lists of anything. So here we abstract int and float to a new type A. And in fact, it can return you a list of anything else, so a list of B's. And now, let's try to, again, write down the definition of these functions, but at all these points where they differ, we write a variable. So, okay, now our function is called f and not square root list or suck list. So how would the first equation look like? The first equation is the same for both suck list and square root list. It says if it's applied to the empty list, then it's the empty list. And if it's applied to the non-empty list, then, now here we have a difference. Here we apply suck, and here we apply square root. So this is the difference, and so we abstract from this difference by using a variable instead. So instead we use a variable for the function that is applied, gx, and then after the colon, this function is called recursively. So f would now be called on axis. So this is the general form of these functions, and of course now this g is a function variable. So this function variable, well, depending on which function you want to have, f will do different things. So this function here should be an additional input to f. Otherwise, we don't know what f does. What f does. So g should be an additional input to f. And what would be the type of g? What do you think? What would be the type of g in order to make this work? Mm-hmm. The type of A to B? Right, A to B. It takes an element of the input list, so it has type A, and it produces an element of the output list, so output list has type B. The elements have type B. So G would have the type A to B. And if we do this, then we get the following function. And this function is predefined in Haskell, and it is not called f, but it's called map. So this is the same as this f, but now we add g as an additional argument. So now this function is called map. What it does is it takes a function g, which has type A to B, and it takes a list where the elements have type A, and it applies this function G on each element of the list. So you get back a list of type B. So what map does is, if you apply map G to a list where you have the elements x1 to xn, then the result will be the list where G is applied to the first element, to the second element, and to the last element. And indeed, it works exactly in the same way as sucklist and square root list, but we abstracted the differences. So this is the same for both sucklist and square root list. And here, well, G in the first case would be suc, and in the second case it would be square root. So this function map implements the general idea of take a function and take a list and apply the function to each element of the list. That is what map does. And well, this function is predefined in Haskell because this is a recursion structure which is very common. But of course, if you identify other forms of such recursion structures, you can implement such higher order functions yourself. Now, what is this good for? Well, we would not implement sucklist and square root list in the way that we did before, but instead we can use the function map. So do you have an idea how to implement sucklist and square root list in a very short way by simply using the function map? Mm-hmm. Exactly. So now sucklist and square root list would be implemented like this. So these are one-line implementations, which is, so I hope. So sucklist is simply the function map suc. That's it. So if you give an argument to sucklist, then what happens is you apply map suc and this list. So if you dislike this curried version, you can also write sucklist of a list axis is map suc axis. So this means this function is defined as apply the function suc on each element of the. And okay, instead of writing this, you can also make it shorter by simply writing sucklist is map suc. And square root list then obviously is map square root. So this means this is the function which applies the function square root on each element of the list. And now you must admit that this definition is shorter than the one above. And if you are familiar with these recursion structures and you immediately know what map does, then if you see this, you immediately understand this definition because, well, you know what map does. So you see, aha, this function applies square root to every element of the list. And this is, of course, much shorter. And, well, use the definition of map every time you implement such an algorithm. Okay, now map is particularly simple. Let me give you another simple example, and then I give you a more complicated one. So map you can very often use, and you can write very short programs in this way. Of course, before I should mention, such map functions you can implement yourself for more or less any kind of data structure. So the general idea of map is apply a function on each component of a composed data structure. So here a function for lists, you apply the function to every element of the list. You can also trees. So if you find, say, binary trees yourself, you can define a function map tree for trees, and then map tree would take a function and apply this function to every node of the tree, or to every element which is stored in this tree. Or if you define graphs, then map, you could implement a map function which implements a function to every node in this graph. So in general, map functions, which are similar to this map, can of course be implemented for data as well. So also for user-defined data structures. And the general idea is always they apply a certain function, a function g, to each component of a composed data object. So something like a list which is composed out of elements. Here you would apply the function g to every element. And for trees you would apply to every node. And so on. for another higher order function which implements a different form of recursion to be. So this you can only do in languages where functions are first-class objects, so where functions can also be arguments. So this you can only do in languages which permit higher order functions. So this will be very difficult to do in languages like Java, for example. And so this is really something which is rather specific to functional languages. Okay, so the next function that I want to show you as another easy example is, again, a predefined function which is called filter. So this is example 2, the filter function. To give you some more feeling how this might look like. So the idea is pretty much the same as in the map example. So again, let's assume we have two functions which look similar but which do different things. Now the idea of these two functions is the following. The function drop even, here the idea is you take a list of integers and you remove those integers which are even. So you just keep those that are odd. So let's look at an example. So drop even. If you give a list of integers to drop even, it will drop those numbers which are even, gerade in German. So the even numbers here are 2 and 4. So you just keep the odd ones. So it will give you 1 and 3. And you do this by using a function odd, which is predefined in Haskell. So let's look how it works. So it takes a list of integers. If it's empty, you return the empty list. If it's not empty, well, then you look. If the first element is odd, then you keep it, and you call drop even recursively on the rest of the list. And otherwise, the first element is even, and then you drop it. So you delete it, and you call drop even on the rest of the list. So you only keep those elements which are odd, and those elements which are even are simply removed. Now the function drop upper does something completely different. Drop upper takes a list of characters, so it takes a string, and it drops the uppercase symbols from the string. So it only keeps the lowercase symbols. So here's an example. So if you give the following argument, so in German, GmbH has a certain meaning. This is, in English you would call this limited. So this is a way to organize companies, and they have limited responsibility for this. Anyway, if you don't understand what this means, then just see it as a string. Now in this string, there are two uppercase symbols, G and H, and two lowercase symbols, M and B. And drop upper removes the uppercase symbols, so it removes G and H. And so the outcome will be the list with these two characters. And how does it work? Well, in a very similar way. If the list is empty, you get the empty list. If it's not empty, you check whether this is a lowercase symbol. The function is lower, is predefined in Haskell. If it's a lowercase symbol, you keep it and you call drop upper on the rest of the list. And otherwise, it's an uppercase symbol, then you drop it and you call drop upper on the remaining list. So now again, if you look at these algorithms closely, you see, well, they somehow look similar. They are implemented in a very similar way, but there are two differences. So again, so the differences are, again, the data structure. So drop even operates on lists of integers, and drop upper operates on lists of characters. So in order to abstract from this difference, we should now write a function which subsumes both, and this function would have to operate on lists of anything. So instead of operating on lists of integers or characters, we should operate on lists of arbitrary elements. And moreover, what do these functions do? Well, they take a list and they throw out all elements which do not satisfy a certain criterion. So they filter out the elements which satisfy odd or is lower, and the other elements are thrown away. And the function that is used for this filtering is odd in the first example and is lower in the second example. So this should be replaced by a function variable called g. And then we can write down the general definition of these functions. So how would such a general function look like? It would be, again, a function f. It takes a list of not integers or characters, but anything, and it gives you back a list of the same data type, but some of these elements are removed, namely those that don't satisfy a certain condition. Now, how is drop even or drop upper defined? Well, if you give it the empty list, it returns the empty list. And if you give it a non-empty list, then we check whether this condition is satisfied or not. Now, this condition is odd in the first case, and it is lower in the second case. So in general, this condition is some function g, which is applied to the first argument. If this g condition is satisfied, so if it returns true, then this x is kept, and this function f is called recursively on the rest. And otherwise, this x is dropped, and f is called recursively on the rest. So this is the thing that these two functions have in common. And now, obviously, here again we have this function variable g. And so g should be another input to this function f, which will turn it into a higher order function again. So map was a higher order function because g is an argument of map. And now this function will also be a higher order function because this g is an argument to f. So what would be the type of g? So g should be an input to f. And what would be the type of g? A to bool. Right. So this is a function which takes an element. This is the first element of the list, so it has type A. And the result type must be bool because, well, these conditions, they must have a Boolean result, and depending on whether it's true or false, you go to this result or you go to the next result. Okay, and by adding this, we get the function that we want. And again, this is predefined in Haskell, and the name for this function is filter. So filter looks like this. So filter takes this function g of type A to bool, and it takes a list of a's and returns a list of a's, but some of these a's are dropped. So how does it work? Well, if the list is empty, then it remains empty. If it's not empty, you check whether the first element satisfies this condition g. If it does, then g is kept. If it does not, then x is thrown away, and filter is called recursively on the list. So what filter does is filter g and x1 to xn gives you the list of those x's in here, so xi1 to xik, where these are between 1 and n, and these xi's are those elements which satisfy g. Are those elements where g returns bool, returns true. Okay, and if we have this filter function, then how can we now implement drop even and drop upper in a short way? So again, this is hopefully rather obvious. So how would you implement drop even using the function filter? Any idea? Mm-hmm.
Drop even equals filter odd.
Right. So drop even is filter odd, and drop upper is filter is lower. You just have to say how to instantiate this function g. So let's see. So drop even is filter odd, drop upper is filter is lower. So this tells you how to instantiate this parameter, this function parameter, and, well, same effect. So this is shorter, more readable and reusable, and if you know what filter does, you immediately understand what this means. This means take a list and filter out those elements which are odd. And this means take a list and filter out those characters which are lowercase characters. So if you know what map or filter does, definitions like this are very easy to read and very easy to write. Okay, now after having seen two very easy higher order functions, I will introduce one last more, and that is a bit more complicated but also very useful. Now again, filter, of course, you can also define for other data structures which you might have written yourself. And again, the idea is you take a composed data structure and filter removes certain components from this data structure which don't satisfy a certain condition. So just as with map, you can define filter on your own data structure as well. Okay, the last example is the function fold. And while we proceed in a similar way, I will again give you two algorithms which somehow look similar. So here we have two algorithms. This time I used not the predefined list, but our own list, because the principle is easier to illustrate with user-defined lists than with predefined lists. Let's see whether we have some more chalk. No. So these two functions do the following things. They operate on our user-defined lists. So the empty list now is nil, and the constructor which adds something to a list, which inserts something to a list, is cons. And what these functions should do is the function add takes a list of integers and adds them all up. So it builds the sum of all the elements. So let's make an example. So if we apply add to, say, the list cons1, cons2, nil. So this is the list. This represents the list where 2 is inserted into the empty list and then 1 is inserted in front. So this is our own definition of list, but it would correspond to this list, 1, 2. Now what add should do is it should build the addition of all these things. So it would compute 1 plus 2, so the result would be 3. So this is 1 plus 2. And prod does something similar, but it builds the product. So if you take the same list, then it would multiply all the numbers in there. So it would compute 1 times 2, which is 2. So this is 1 times 2. So this is the difference. This function adds all the elements in a list. This function multiplies all the elements in a list. Now, how do they operate? Well, okay, this function, if you give it the empty list, it gives you 0. Because, well, if you sum up all elements in a list and the list is empty, if you then sum it up, you get 0. And if you have a list which is not empty, then you call plus with the first element and the sum of the remaining elements. So this will sum up all the elements. And now prod works in a slightly different way. If here you get the empty list, you don't return 0, but you return 1. And if the list is not empty, you take the first element and multiply it with the result that you get by multiplying the rest. So particularly if you have a list with just one element, then here you would multiply this element with prod of the empty list. Prod of the empty list is 1. So you would get exactly this single element in the list. So it's a good idea to use 1 here and not 0. Otherwise, if you use 0 there, then the result of prod would always be 0. That is not what you want. So more precisely, for an argument which would look like this, so it would be a list which starts with cons. Then here we have the first argument. Then have cons. Here we have the second argument, and so on. Here we have cons and the nth argument. This would be inserted into the empty list. So this is this represents the list with the elements x1, x2, x3 until xn. And now, what would be the result? So add gives the result where, well, what do we get? If the list looks like this cons is replaced by the function plus, and then add is called on the rest of the list. So if add is called on the rest of the list, this cons is also replaced by plus, and then add is called on the rest of the list. So this works on until we reach this cons, and then again, if we reach this cons, add will replace it by plus, and then add is called on the empty list nil. And now, if add is called on the empty list nil, the result will be 0. So in other words, what add does is, it takes the original list, but each data constructor is replaced by something new. The data constructor cons is replaced by plus, and the data constructor nil is replaced by 0. Now let's look at what prod does. If you call prod on the same list, this cons would be replaced by times. So you would get times x1, and then prod would be called on the remaining list. What would it do? It would replace this cons by times as well, and then it would be called on the remaining list. And then finally, this last cons would also be replaced by times, and then times would be called on the empty list nil. If times is called with the result nil, the result will be 1. So again, you can see what prod does is it replaces the data constructors cons and nil by new functions times and by 1. So what we can see is add and prod replace the data constructors of our data structure, namely lists, the data constructors cons and nil, by new functions. So we basically keep the term structure, but cons is replaced by plus in the one case and by times in the other case. And here, nil is replaced by 0 or by 1. So replace cons by plus or by times, depending on whether you use add or prod, and replace nil by 0 or by 1, depending on whether we use add or prod. Okay, and when we see this, then we get an idea how to abstract from add and prod and to define a function which does something more general. Because we can see what the difference is between add and prod. They both replace the constructors of our data structure by new functions or by new values, but by different values. So let's abstract this to a function variable, g, and let's abstract this to a variable of type integer, let's call it e. And then one times g will be instantiated with plus and one times with times, and e will be instantiated by 0 or by 1. So if we see this, then we suddenly see how a general function would look like, which does the same as add or prod, but which is more general because instead of plus or times we use g, and instead of 0 or 1 we use e. So a general function would look like this, and again, we do not only define it for lists of integers, but we just define it for lists of any type A, and the outcome can be any type B. So if you apply this to nil, then what would happen? Well, for add, we would get 0. For prod, we would get 1. So in other words, this is the value that we replace the constructor nil with. And now we wanted to make it more general. We wanted to say we replace nil not by 0 or 1, but by a new variable e. So here the result should be e. It should be 0 if we want to simulate add. It should be 1 if we want to simulate prod. And if we call f with cons, with this, then, well, again, we write it in the same way as we wrote it over there. So now we replace this cons by a new function, either by plus or by times, but to make it more general, we replace it by a new function g. So g, and then g is applied to x. As you can see, we have plus x or times x, and then this function is called recursively. So now we write f(x)s. So by abstracting from the differences between at and prod, we get this new function. And now, of course, here we have this e, and here we have this g. So this e and this g should be additional parameters of f. So what would be the type of e? And what would be the type of g? What would be the type of e? Yeah. Must be b. Right, the type must be b, because what f does is it takes a list and gives you back an object of type b. And this tells you how this object looks like if the list is empty. So e must have the type b. In our example, both a and b were int. So if you want to have an integer in the end, then b is int, and then e must be an integer. And indeed, here it is an integer, so it is 0 or 1. And what is the type of g? So in order to find out the type of g, let's look at the type of this. The type of this is what? A. It's a list of a's. Now, what is the type of the second argument? The type of the second argument is, well, this is f applied to a list, and if you apply f to a list, it gives you b. So this is b. So in other words, g gets two arguments. First argument of type A, second argument of type B. And so first argument of type A, second argument of type B. And then what is the type of the result? Must be b. So that's it. In our example, a and b were the same. So both a and b were integers. So there the g had the type int to int to int. And indeed, this is the type for both plus and times. So this is indeed correct. So by adding e and g as additional inputs to this function, we get what we want. And this function is predefined for the predefined lists. Of course, if we define lists ourselves, then it's not predefined. Then we have to define it ourselves. And it would look like this. So ignore this function concat for the moment. I will speak about this function later on. Just look at this fold function. So this function fold, we would now define just like f, but you would add these arguments. This is the g argument, and this is the e argument. So g has the type a to b, e has the type b, and if we give these two things to this fold function, then we indeed get a function which takes a list of a's and gives a b. And now the definition is as on the blackboard. So now we have these additional arguments, g and e, but the rest is the same. So if we apply the whole thing to nil, we get e. If we apply the whole thing to cons x-axis, we get g, x, and the recursive call. The only difference to the blackboard is that we added these additional parameters, g and e. And now with this definition of fold, so what fold does basically is, so the idea of a fold function on any data type, on any data structure is replace the data constructors of this data structure by new functions. Replace the data constructors by new functions. So in other words, if your data, the number of arguments of fold is, for every data constructor, you have one argument, and then you have one additional argument which takes the whole object. So list has two data constructors, namely cons and nil, and therefore fold has one argument which corresponds to cons. So const should be replaced by this function. Then it has another argument which corresponds to nil. So nil should be replaced by this value. And then it has one last argument which corresponds to the whole data object. So we want to have a fold for lists. So this would be the list which is modified, and then it has some result, namely this result thing b. So as you can see here, we've modified this list, but we need additional arguments for each data constructor. This one corresponds to const, this one corresponds to nil. So you can write something like this on any data structure you like. Now, how would we now implement add and prod in a short way using fold? So, yeah, I guess you know it again, but maybe someone else knows it as well. It's very similar to the way we did it before. Now we call fold, but we have to say how to instantiate these parameters of fold. So we have to say what G is and what E is. So what is G in this case, and what is E in this case? Mm-hmm.
Fold of plus
Mm-hmm.
and 0.
Right. So here it would be fold of plus and 0, and here it would be fold of times and 1. So that's indeed how it looks like. Fold of plus 0 and fold of times 1. So in other words, this means add does the following thing. It replaces the constructor const by plus, and it replaces the constructor nil by 0. And here prod replaces the constructor const by times, and constructor null by 1, nil by 1. So that's what this means. And to give you one more example where to use fold for, I wrote down this concat algorithm as well. So concat really does something which looks completely different to what add and prod does. I mean, add and prod really look rather similar, but concat probably does not look so similar. So what this concat function should do, concat takes a list of lists and unites all these lists in the list. So if you write it with a predefined list, it would do something like this. If you take a list containing maybe these 3 lists. So this is a list with 3 elements. First element is the list 1, 2, then the list 3, then the list 4, 5, 6. It would unite all these lists and give you the list 1, 2, 3, 4, 5, 6. So this concat function is predefined on the predefined list, but we can also define it on our own lists. So on our own list, it would look like this. It takes a list where the elements are again lists, and it gives you a list back where the elements are just of type A. So what would it do? If you give it the empty list, it gives you the empty list. Otherwise, so if this is the first list in this list of lists, this X, and these are the remaining ones, it would append, so concatenate, it would append this first list to the result of applying concat to the rest of the list. So append simply takes 2 lists and adds them after each other. And now, if you look at this closely, you see what happens. The constructor nil is replaced by nil, and the constructor const is replaced by append. And that's it. That's all that concat does. So you can also define concat in a much shorter way. You can say concat is the function which replaces const by append and nil by nil. So by using this fold declaration, you can write it down in one single line. And although concat really seems to do something which is rather different from add or prod, you can see it follows the same recursion structure, and therefore we can implement it with the same function fold. And so this gives an idea how this fold is used for actual data types. Now, as I said, for predefined lists, this fold function is already there. So for predefined lists, fold is already also predefined. And there it is called fold R. So fold to the right, there's also a fold L function which implements another typical recursion structure. And, well, if you want to see how it looks like, I can rewrite all these definitions with predefined lists, then it would look like this. So this is exactly the same thing that we had before, but now I use predefined functions. This function add is in fact also predefined on the predefined list, and it's called sum. So this was used to sum up all the lists. This sum all elements of the list. This multiplies all elements of the list, and this concatenates all elements, provided these elements are lists themselves. And now fold R, this is predefined. It's the same as the fold function I just showed you, only on predefined lists. And then again, you can program sum, prod, and concat in one line using these functions. Here, you replace the list constructor colon by plus and the empty list by 0. Here you replace colon by times and the empty list by 1. Here you replace colon by the append function plus plus and the empty list by the empty list. So this gives you an idea how to use these higher order functions. And as I said, you can also write such fold functions on other data structures. For example, you can just as well do this on trees as well. And right, so before I forget, the next lecture on Tuesday does not take place because there's DS, there's Fachschaftsvollversammlung. So there is no lecture on next Tuesday, but there's exercise on Wednesday. And next Friday will be the next lecture. Okay, have a nice weekend.